Hello everybody, welcome to this fifth lecture. Our topic today is lecture 5 and the title is Special Contours. So what we are going to do today is we will see some more integrals that can be computed using the residue theorem, and computing these integrals will involve integrating a homomorphic function on particular contours. The choice of these contours will vary depending on which function we would like to integrate. In our first example is we would like to compute the integral from minus infinity plus infinity of sine x divided by x in dx. Okay? This improper integral. So, first of all, notice that here there is an apparent singularity at the origin, but this is actually a removable singularity even for the function sine x over x defined on the whole the complex line. So in particular, on the real line, this function extends to a continuous, even a smooth function, also at 0. So the question of the existence of this improper integral concerns only the behavior of this function at plus and minus infinity. And so this is exactly the example we discussed in our meeting. We saw that sine x over x is not summable, so the integral of the absolute value of sine x over x diverges. However, the integral of sine x over x does converge, and this can be shown, for instance, by partial integration to show just the convergence of the integral, not how to determine the value. So, in order to compute this integral, so this is an integral which is similar to those that we treated last time and we labeled as type 3. So it's sine x multiplied by a rational function where the denominator has degree at least one more, in this case exactly one more than the numerator. The rational function is simple 1 over x. However, here the difficulty is that the rational function now has a pole on the real axis, whereas in type 3 we were assuming that the rational function had no poles on the real axis. So we'll have to do something slightly different. Namely, we will again look at the map f of z at the homomorphic function e to the iz divided by z, and we will observe that this is homomorphic on c minus the origin. So we have a singularity at the origin just because of this denominator, and we can also easily compute the residue there. The residue of f at the origin is, we multiply by z and evaluating z equals 0 and obtain 1. Okay, now let's draw the contour on which we are going to integrate. So we said there is a singularity at 0, so our contour cannot be, as in type 3, a rectangle passing through 0. We have to avoid this singularity. So what we will do is the following. We will straight, then the small arc of a circle will avoid the singularity, then go on, and then again we will do we'll consider the same rectangle that we consider also in integrals of type 3. So here, this is r, let's say big R, this number here is IR, so that this length is also R, and so this is minus r. And here we will consider a very small circle, say of radius 1 over r. Okay, and then the parameter r will go to infinity, so this arc becomes smaller and smaller, and as usual everything is oriented counterclockwise. Okay, and let's call gamma 1, gamma 2, and gamma 3 these pieces, and then we will use some other notation to denote the other pieces of this contour. Now, this contour is now enclosed in no singularities. The only singularity of our function is at 0, and this is outside of the region bounded by the contour. So we can say that the integral of our function e to the I z divided by z in dz on this contour gamma is 0. This we know. Moreover, arguing exactly like the integrals of type 3, we know that the integral over each gamma j, either gamma 1, gamma 2, or gamma 3, all of these integrals tend to 0 when r goes to infinity. And this is exactly the same argument that we used for integrals of type 3, and it's based on the fact that the rational function 1 over z goes to 0 like 1 over r when the absolute value of z is r. Okay. Then we have to deal with these two intervals on the real line and with this half circle. So I keep the picture here. Now we get some space to compute the other pieces we are interested in. So, first of all, let's consider the integral over the interval minus r minus 1 over r union, then we do this 1 over r comma r of our function e to the I z divided by z in dz. Okay, this is precisely, so we can write, so now z is real, so we can also call it x, and we can write e to the ix as cosine x plus I sine x, so we can split this integral in 4 pieces. We will have is integral from minus r minus 1 over r, and here we have cosine of x divided by x in dx, and then the integral of the same function but on this interval, so integral from 1 over r to r cosine x divided by x, and then you have the imaginary part plus I, and we have the integral between minus r and minus 1 over r of sine x divided by x, and the integral between 1 over r and r again of sine x divided by x in dx. Okay, now these two integrals, so cosine x divided by x is an odd function, because cosine is an even function and x is an odd function, so the quotient is an odd function. And here we are integrating this odd function on an interval, and here minus the same interval. So these two integrals are, one is minus the other, so the sum, so they cancel out. So for every r, these two terms are opposite, so the sum is 0. Now what happens when r goes to infinity? So when r goes to infinity, here this interval is invading the negative real axis, and this interval here is invading the positive real axis. So this integral will just convert to I times the integral from minus infinity to plus infinity sine x divided by x in dx. Okay? Since we already know that this function has a converging improper integral, then the improper integral can be obtained as a limit, for instance, in this way. Okay, so notice that instead the limit for r going to infinity of each of these two pieces separately would diverge, because here cos x divided by x, this has a singularity at 0, and at 0 this is diverging like 1 over x, and 1 over x is not integrable near 0. Okay, so the sum is 0 for every r, but separately each of these two integrals would diverge. One goes to plus infinity and the other one goes to minus infinity. Okay, but in total this integral converges for r going to infinity to I, the integral we are interested in. So the last bit that we have to analyze is the integral over this half circle. And let's do this a bit more generally, because then we will have a criterion which can be used also in other cases. So let's prove the following lemma. Let's say that f is a homomorphic function with a simple pole at z0. Okay, so here it's important that the pole at z0 is simple. And then we want to integrate over a circle, so this is z0, and we consider an arc of a circle corresponding to some angle theta, and the radius is r. Okay, so gamma r is this path. It spans an angle theta, and the radius is r. And what I'm saying is that the limit for r going to 0 of the integral on this gamma r of f of z in dz, this is theta I times the residue of f at z0. Okay? This is the value of the limit. Theta I times the residue of f at z0. Notice that, so this formula generalizes something that we already know. So if we integrate over the whole circles, then theta would be 2 pi, 2p, and then this integral would converge to 2pi times the residue. Okay? In that case, actually, the integral equals this quantity for every r, and in that situation is also the information that the pole is simple is also not relevant. This could be any isolated singularity. And instead, for an open arc, for a non-closed arc, it's important to take the limit, and it's important to assume that the pole is simple. Okay, how do we prove this formula? We can just write down the Laurent series expansion of f at z0. So the pole at z0 is simple, so it means that the principal part of the Laurent series is just the residue at z0 divided by z minus z0. And everything else is just regular part. Then there is plus g of z, where this is regular, so g extends for holomorphic function on a small disk centered at z0. On D, say this is a disk centered at z0. Okay? This function g is not singular at z0, the singularity is removable. Okay, we have this, and then we know that since g is holomorphic on a disk, we also know that it admits a primitive, a holomorphic primitive. So call big G a holomorphic primitive of small g on the disk. Then when we integrate f of z over this gamma r, we'll obtain. So when we integrate this function, this is the usual computation that we've done several times, and so the contribution of this integral on this angle spanning an angle theta is precisely theta I times the residue of f at z0. Okay? So here we're using the fact that when we integrate 1 over z minus z0 over an arc spanning an angle theta, the result is theta I. And then everything is multiplied by this complex number, the residue of f at z0. And the integral of the function small g can be expressed as, so if we call these two endpoints of the path AR and BR, this is the integral of small g over this path is just big G at BR minus big G at AR. And now let's see what happens when R goes to 0. BR and AR, they both converge to Z0. And the primitive big G is well defined, it's a continuous function also at Z0, so this difference goes to 0. They both converge to G of Z0. So if this goes to 0, here we find exactly theta I times the residue. So this proves the lemma. Okay. Now that we have the lemma, we can go back to our situation. see again what we have. Okay, recall that we were integrating over a contour having this form. And we were using the identity that the integral over this contour of our function e to the I z divided by z in dz is 0. And then we have also said, so the integral on these three sides converges to 0, whereas the integral on this, let's put again, minus r, minus 1 over r, 1 over r, big R, the integral on from minus r to minus 1 over r union 1 over r, comma r, or function e to the I z divided by z dz, we show that this converges to I times the integral we are interested in, minus infinity plus infinity sine x over x in dx. And the final piece is what is the integral over this. I won't give it a name, I will just draw the picture. What is the integral of e to the I z divided by z in dz? So this is the integral on an arc, along an arc, and arc of a circle, but this is now parameterized clockwise. So to reduce to the situation of the lemma, let's put a minus and let's parameterize the same arc counterclockwise. So we have e to the I z divided by z in dz. And now when r goes to infinity, the radius of this half circle, 1 over r, goes to 0. So when r goes to infinity, we're exactly in the situation of the lemma. We're integrating a function which has a simple pole here at the origin, in this case. Our function has a simple pole at the origin, and here we're integrating it on a small arc spanning an angle P. When the radius of the small arc goes to 0, equivalently when big R goes to infinity, everything converges to Pi times the residue at the origin, which we have shown to be 1, and then we still have this minus in front of the integral. Okay, so this part, this integral converges to I, the integral we are interested in. The integral here converges to minus Pi, and the integral on all the other pieces go to 0. And in total, the integral over the whole contour is 0, no matter how large the contour is. So if we put all these pieces of information together, we obtain that this integral equals minus this quantity. And by taking imaginary parts, we obtain that the integral of sine x divided by x in dx from minus infinity to plus infinity has the value p. Okay, so we have computed the value of this improper integral. Okay, this was an example in which we had So it was almost an integral of type 3, but we had a singularity at the origin, so in a point of the real axis, and we just modified our rectangle so to avoid the singularity by going around this small half circle. Okay, let's look at another example. Example 2. Now we would like to compute the integral from 0 to plus infinity of x divided by 1 plus x to the power 4 in dx. Okay. So this is similar to the integrals of type 2, but now we want to integrate only on a half line. And so it would not help to integrate this function over the whole real line, because this is an odd function, so the integral over the whole real line is just 0. So it gives us no information. And hence we will do something else. But first of all, notice that here we have no problem in summability. This function goes to 0 when x goes to infinity, like 1 over x to the power 3, so it's clearly summable. And this time we will integrate over a half or a quarter of a circle. More precisely, we will integrate over this contour. So this is the point R, this is the point IR, and we will consider this contour. And again, we have the contributions gamma 1, gamma 2, and gamma 3. So, and the function f of z is, of course, z divided by 1 plus z to the power 4. So, this function has 4 singularities. It has 4 simple poles at the 4 fourth roots of minus 1, and only one of those is contained in the interior of our contour, and this is the singularity at e to the power I pi over 4. Okay, so we can immediately say that the integral over the whole contour gamma of z divided by 1 plus z to the 4th dz is 2pi times the residue of this function f at e to the I p divided by 4. Okay, so first of all, we would like to compute this residue. So this function f can be rewritten as, so this is z divided by, so here we have z to the 4th plus 1, and this can be decomposed as z squared plus, or minus I times z squared plus I. Okay? And then here, the 2 square roots of I are precisely, one of them is our pole inside the region bounded by the contour, and the other one is minus it. So this we can split as z minus e to the I p divided by 4, z plus e to the I p divided by 4. And this piece, we can also leave it all together without factorizing it. This is z squared plus I. Okay, And then now from this expression it's easy to compute the residue. The residue of f at e to the I p over 4 is, you have to multiply by z minus e to the I p over 4, and this cancels, and then we have to evaluate at e to the I p over 4. So we obtain e to the I p over 4 above, and here e to the I p over 4 plus the same thing is twice e to the I p over 4, and z squared e to the I p over 4 squared is I plus I. We're multiplying by another 2I. Those two cancel, and we get 1 over 4I. Okay, so the value of the residue is 1 over 4I, and we conclude that our integral has the value p half. Okay, 2p divided by 4, and I cancel out. P half. Okay, so this is the value of the whole, of the integral of the whole contour. Let's keep it here. And now let's analyze the different pieces. Well, the integral on gamma 1 of our function z 1 plus e to the 4 dz, this is the integral on the, is just integral from 0 to r x 1 plus x to the 4th dx. This is the part we're interested in. Actually, we're interested in understanding its limit for r going to infinity. The integral over gamma 2 z divided by 1 plus e to the 4 dz, this goes to 0 when r goes to infinity. This is the usual computation that we did when treating integrals of type 2, right? Here the denominator has degree 4, the numerator has degree 1, so this function goes to 0 when z goes to infinity, like 1 over z to the power 3. And when we integrate over this arc, which has length which goes to infinity like absolute value of z, we get something like 1 over r squared. So it will go to 0, exactly as we saw for type 2 integrals. There remains to look at this integral over gamma 3, the integral over gamma 3 of z I plus z to the 4th dz. So on this line, z is nothing else but I times y, where y varies, is real now and varies between 0 and r. But this integral is, we go in the direction of decreasing y's. So this we can rewrite as minus the integral from 0 to r. And instead of z, we plug in I, y. So we have I, y divided by 1 plus I to the power 4 is 1. So here we get 2y to the power 4. And dz is I dy. I dy. So this I here and this I here, they multiply and give us minus 1. With a minus, we get plus 1. So this integral is again integral from 0 to r, y 1 plus y to the power 4 dy. So in other words, the integral on this interval, this piece of contour, and the integral on this piece of contour, oriented this way, they coincide. So these two things are the same. Then we obtain that the sum, this integral, plus this integral, which is just twice this, plus something which is going to 0, must give us p half. The conclusion is that the integral we are interested in, so the integral between 0 and plus infinity of x 1 plus x to the power 4 dx is just half of p half, so it's p over 4. Okay, again, because this integral equals twice this integral plus something which is infinitesimal in r. So when we take a limit for r going to infinity, we obtain twice the integral from 0 to plus infinity plus 0 equal p half, then we divide by 2 and we obtain the desired formula for our integral. Its value is p over 4. Okay. So this was an example in which, we integrated on we wanted to integrate on a half line, and we could do it by integrating actually on a quarter of a full circle. Let's sketch briefly another example. Which is again based on, in this last integral we saw that on our contour, we decomposed our contour in several parts, and in some parts the integral was going to 0, and in some other parts the integral was, for instance, in this case we found it was exactly the same integral we were interested in. Okay, so we were able to compute our given integral by such an analysis. And a similar case is if you want to compute, so this is example 3, we would like to compute the integral from minus infinity to plus infinity of, let me write it here, this is e to the ax divided by 1 plus to the x dx, where a is between 0 and 1. It's a real number and it's strictly between 0 and 1. Okay, first of all, notice that the fact that a is smaller than 1 gives us the fact that this function for x going to plus infinity goes to 0 exponentially. It goes to 0 like e to the power e to the power a minus 1 times x. So it's exponential conversion to 0, so we get some ability on that side without any problems. And also when x goes to minus infinity. When x goes to minus infinity, the denominator converges to 1, and e to the ax goes to 0 exponentially because a is positive. Okay, so this function is summable. We have no problems of summability. And now to compute this integral, we would like to look again. So we want to look at the holomorphic function f of z equals e to the a z divided by 1 plus e to the of z, and we will integrate this function on a contour which is a rectangle of width to r, so this goes from r, and here we have minus r, but here the height is just 2pi. Okay, meaning that this point here is now r plus 2pi, and this will be minus r plus 2pi. And as usual, we orient everything counterclockwise. So, this function has poles when the denominator vanishes, and here the denominator vanishes when e to the z is 1. In other words, when z is pi plus multiples of 2pi. So here inside the region contained, bounded by the contour, we have just one singularity at the point pi, here in the middle. Okay? And then you can compute easily that the residue of our function f at such a singularity, pi, is minus a e to the power a p I. Okay, it's a simple pole, and this is the value of the residue. Then let's call these sides again gamma 1, gamma 2, and gamma 3. The other things you can check easily is that the integral over gamma 1 of fz dz goes to 0. And the same is true for the integral over gamma 3 fz dz. Okay. After all, these are just integrals on paths whose length remains bounded. The length is 2p. Okay, because when r goes to infinity, this interval, this rectangle becomes longer and longer, but the height remains 2p. So they have length 2p, but the function f on them, you can show that it's going to 0 uniformly. Okay, we have this. And then it remains to understand what is the integral over gamma 3 of f of z dz. And here, by parameterizing this interval in the obvious way, you parameterize it by x, by the real variable x, writing z equal x plus 2pi, you will, after some computations, you will get this formula. This is minus e to the 2api times the integral between minus r and r, the integral we are interested in, but between minus r and r. So e to the ax divided by 1 plus e to the x dx. Okay. Now here one has all the information to conclude the computation. So we get the equality that 2pi times the residue of pi, so times minus, so there is a minus and there is an e to the power a pi. This equals the value, the integral over the contour, and then of course then also the limit of the integral over the contour as r goes to infinity, and these two terms do not contribute. This term contributes exactly for this value, and this other term, by this identity, contributes for this value but multiplied by this number. And so we obtain that this is equals 1 minus e to the 2a t I that multiplies the integral we're interested in, minus infinity plus infinity e to the ax divided by 1 plus e to the x dx. Okay, and then, so this number is non-zero, so you can just divide by this, and you find the value of the integral. Again, a small computation will produce p divided by sine of a p. Okay, so here was a bit fast, but if you look on the book of Howe, you will find full, complete computations to reach this result. Very good. So again, this was also an example in which we had a domain, we had a contour, and on this side of the contour, in this case, there was a sort of phase shift. The integral here is not precisely the same integral we started with, but it's the same integral multiplied by this number. But this again allows us for computations, allows us to conclude. So let's finish today's lecture with computing some important integrals that are known as Fresnel integrals. Namely, we would like to understand the value of the integral between minus infinity and plus infinity of e to the I x squared in dx. Or equivalently, by separating the real and imaginary part, this is the integral of between minus infinity and plus infinity of cosine x squared dx plus I integral between minus infinity and plus infinity of sine x squared dx. Okay, we want to compute all these integrals. Notice that this function cosine x squared, sine x squared, or the complete one e to the I x squared, they are not summable. For instance, here it's clear to see that it's not summable. If I take the absolute value of this function, this is 1. Okay, so integrating 1 over this over the whole real line, we obtain plus infinity. Okay, but nevertheless, so these are not summable, but nevertheless, their improper integral converges. Okay? This could be proven by the usual method, by the usual partial integration. If you just want to compute, you want to show that these integrals do converge. But actually, it will also come out as a consequence of our computations. Okay, we have these Fresnel integrals. And here the idea is to erase them, so I will need a bit more space. So here we will look at the holomorphic function f of z equals e to the I z squared. And this now is a function which is holomorphic on the whole complex line. So this is an entire function. And we will integrate this entire function over this contour. We go from 0 to r, and then we look at an arc of a circle of radius r, and here the angle is pi over 4. Okay? So this is 1/8 of the whole disk of radius r. In other words, this point here is r times e to the I p over 4. And as usual, the contour is parameterized in this way, and these pieces are called gamma 1, gamma 2, and gamma 3, and the whole contour is called the gamma. So, this is a holomorphic function everywhere, so clearly the integral of f of z dz over the whole contour gamma vanishes. And the integral over gamma 1 is what we're interested in, f of z in dz. This is just the integral from 0 to r e to the I x squared dx. Let's compute the integral over gamma 3 first. Integral over gamma 3, f of z dz, or maybe let's write immediately what the function is, e to the I z squared dz. So, how do we parameterize this gamma 3? So we can write a minus, and then we will look at actually at the curve gamma 3 hat. Gamma 3 hat is parameterized in the same interval, but the same segment, but in this direction. And the parameterization is just gamma 3 hat of s. This is s times e to the I p over 4. And s varies between 0 and r. Okay, this expression parameterizes this segment, but starting from here and ending here. So here we get a minus sign, and then we get an integral between from 0 to r, and here we have e to the I. So z is s times this, so here we have s times e to the I pi over 4, and this is squared, and dz is e to the I pi over 4 ds. Okay, let's go on. So this number comes out, we can write minus e to the I p over 4 integral from 0 to r. So now we have to square this product. E to the I p over 4 squared, e to the I p over 4 is here. When we square it, we obtain exactly I. Okay, this is a square root of I. And I times I is minus 1. So here we get e to the minus s squared ds. And this function, e to the minus s squared, is of course integrable, has a converging improper integral on the half line 0 plus infinity. So when r goes to plus infinity, this will convert to minus e to the power I p over 4 integral from 0 to plus infinity e to the minus s squared ds. So this is another important integral, and the value, so here now we will use the following fact. The integral from minus infinity to plus infinity of e to the minus x squared, the integral of this Gaussian function over the whole real line. This is of course twice the integral from 0 to plus infinity, because we are integrating an even function e to the minus x squared dx, and this value is square root of pi. Okay, this is the integral of the Gaussian function over the whole real line. So there are actually several ways to prove this formula. One way that you probably have seen is you could deduce it from the change of variable formula for double integrals by computing the integral of the function e to the minus norm of x squared on R2 using polar coordinates. This is one easy way to get this result. It's actually possible to prove this identity also using the complex analysis and using the residue theorem. And in the book of Howe, you find a very nice proof of this formula using complex analysis. One has to integrate over a quite unexpected contour to do that. Okay, but here we will just use this information. So this integral now on the half line is then, so this number we keep is minus e to the I p over 4, and this is the square root of p divided by 2. Okay, so let's see what we have. The integral here is the integral we are interested in. It's written here, integral of gamma 1. The integral over gamma 3, we computed it, it's square root of p divided by 2 times minus e to the I pi over 4. The last thing we have to do is to estimate the integral over gamma 2. We'll actually show that the integral over gamma 2 goes to 0. So assuming that we know this we will check in a moment, let's summarize what we have. I think then we can erase here. So let me write again. What we will show is that the integral of our function e to the I z squared z over gamma 2 goes to 0 when r goes to infinity. Once we will have that, we can now put all the pieces together and we get, so the integral over the whole contour is 0. So 0 is the limit of this integral, which we said is the integral we're interested in, 0 plus infinity e to the minus e to the I x squared dx. Then we have another term, but this goes to 0. So the other limit is plus 0. Plus the integral over gamma 3, which is a minus e to the I over 4 square root of p divided by 2. Okay? So this identity implies, here, now I can get rid of all of this. So here we see that the integral we are interested in, 0 infinity e to the I x squared dx equals square root of p divided by 2 times e to the I p over 4. So this is the value of the Fresnel integral e to the I x squared on the on this half line, and by taking the real part we obtain the integral between 0 and infinity of cosine x squared dx. The real part of e to the I p over 4 is square root of 2 divided by 2. So we get square root of 2p divided by 2, divided by 4. It was square root of 2 divided by 2, yes, square root of 2p divided by 4. And the integral of sine x squared dx is the imaginary part of this complex number, and it's the same. Okay? So these both integrals coincides, which is also probably not that obvious from their definition. Both integrals coincide, and this is their value. Okay? But in order to conclude this computation, we still need to show that the integral over gamma 2 goes to 0. So let's do it. So gamma 2 is this arc, it's an arc of a circle. Gamma 2 can be parameterized as gamma 2 of theta. This is, the radius is r, and here we have e to the I theta. And theta varies between 0 and pi over 4. This is a curve parameterized in this path gamma 2. So the integral over gamma 2 of the function e to the I z squared in dz can be written as integral from 0 to pi over 4 of e to I. So z is this number, so it's r squared times e to the I theta squared, so times e to the 2 pi theta in dz. dz, so this is a function of theta, dz is r I e to the I theta in d theta. And here we can ri, this is a constant, we can take it out from the integral. This is ri, and this we can write it as integral 0 pi over 4, and this is e to the I r squared, and e to the 2I theta, let's write it as cosine of 2 theta plus I sine of 2 theta. And we are still multiplying everything here by e to the I theta, and there is a d theta. Okay, what is this? This is r I integral from 0 to pi over 4. Let's write this exponential or sum as a product of the two exponentials. So we have, let's write first the one with I times I is minus 1. So we have e to the minus r squared sine 2 theta. And then we have the bits with I e to the I r squared cosine 2 theta e to the I theta d theta. Okay. We would like to show that this quantity goes to 0. And here we can just bound, so the integral, this integral of gamma 2 is e to the I z squared dz. Okay, so this, the absolute value here is lesser or equal than, here we can write, so absolute value of r is r, and here we can bound the absolute value of an integral is less or equal than the integral of the absolute value. So here we can write the integral 0 p over 4, and the absolute value of the integral, so this has absolute value 1, this also has absolute value 1, and this is a positive function. So we just find e to the minus r squared sine of 2 theta in d theta. Okay, so here we see something, r is going to infinity, but then we are multiplying this by this integral, which is probably going to 0, since here we have e to the minus some positive function times r squared. But we need to check this fact. Check that actually the product will still go to 0. So let's get some space. So, writing down exactly what this integral is of course not easy, but we can try to bound this integral. And we can bound this integral, for instance, by replacing this sine function, which is somehow the difficulty here. We have e to constant times sine. If we replace sine by a linear function of theta, because then it will be just the integral of an exponential, and this is something we can compute. So if we look at the function sine over 2 theta between 0 and p over 4, okay, here I'm plotting the graph of sine of 2 theta. So at p over 4, 2 theta is p half. So sine has achieved its maximum in the 1. Okay? And then it will go down again. And the sine function on this interval is a concave function. So in particular, it's above this linear function, say, between 0 and p over 4. So we have the inequality sine of 2 theta is greater or equal. What's the equation of this linear function? Here the angular coefficient is 1 divided by p over 4. So this is 4 divided by p times theta. Okay, so from the concavity of the sine function on this interval, we deduce this inequality, which holds all theta in the interval 0 p over 4. Now, thanks to this inequality, we can go on with the estimates. So this is less or equal than r integral 0 p over 4. So here we have e to the minus r squared sine. But sine is bigger than this, okay? And the function e to the minus r squared x is monotone decreasing. So this is less or equal than e to the minus r squared. Instead of sine, I can put this 4 over pi theta, because we have this inequality, and this inequality holds exactly on this interval, which is also the interval on which we are integrating in d theta. And this is now a nice integral that we can just compute. So we have r. Primitive of this is p divided by 4r squared with a minus times e to the minus r squared for p theta. And this has to be evaluated between 0 and p over 4. Okay, and then let's get some space. This equals r times, we get, for r equals 0, we get, sorry, this is for theta. For theta equals 0, here we get 1, so here we get p over 4 r squared minus p over 4 r squared times, when theta is p over 4, you will obtain an e to the power minus r squared. In total, this is p divided by 4r, and this is multiplying 1 minus e to the minus r squared. So now, when r goes to infinity, this exponential goes to 0, so this quantity is converged into 1, but this is multiplied by p divided by 4r, which is now going to 0. So everything goes to 0. Okay? So this shows that the integral over gamma 2 converges to 0 when r goes to infinity, and this was the last part we needed to check in order to finish our computation. Okay, that's it for today, and we'll talk online via Zoom very soon. Bye-bye. Let's do it again. At the origin, and